Hi guys, in my previous lecture I tried to explain about Wheatstone's bridge and Wheatstone's bridge balanced condition. When bridge reaches to balanced condition means current through galvanometer goes to 0, then the ratios of resistance equal to 0. So we saw the Wheatstone's bridge. So Wheatstone's bridge structure always not like as we saw. So this is one of the equivalent circuit of the Wheatstone's bridge. So at here the given problem is that find the magnitude of resistance X in the circuit shown in figure when no current flows through the 5 ohm resistance. So the problem is telling that through 5 ohm resistance current is not flowing. So that is one of our Wheatstone's bridge condition also. So as I said, this is the equivalent circuit of Wheatstone's bridge. So if I draw this circuit as like Wheatstone's bridge circuit, so this is how it looks like. This is the equivalent circuit of the Wheatstone's bridge. So the circuit which is given is exactly equal to the circuit which I draw. In the problem, they are telling that the current through the 5 ohm resistance is 0. When no current flowing through 5 ohm resistance. So in this case, if no current is flowing through 5 ohm resistance, we can apply the ratios of resistance. So if you remember that formula as P by Q equal to R by S, it is the Wheatstone's bridge condition. Just apply the ratio at here. So if I apply the ratio at here, so if I take this P, Q, R, S. So P by Q that equal to X upon 18 equal to R equal to 2 upon 6. Now get the value of X. X equal to 18 times 3. So that is 2 by 6 times 18 which equal to 6 ohm. So the unknown resistance value here we need to find, so that is 6 ohms. It is 6 ohms. So here it was very simple until unless if we do not recognize the given network is the equivalent circuit of Wheatstone's bridge. So once if you recognize that the given network is equivalent to Wheatstone's bridge, so then we can apply easily the Wheatstone's bridge principle. Let's see one more problem, same the equivalent circuit. So here is given the problem. It contains 5 resistance, a big network. So we need to calculate the current draw from the battery by the network resistor shown in figure. So we need to calculate how much current is drawn from the battery of potential difference 4 volt. So this circuit is also equivalent to Wheatstone's bridge principle. Wheatstone's bridge circuit. So let me draw for a moment the Wheatstone's bridge circuit for given network. This is the equivalent resistance, equivalent circuit for Wheatstone's bridge. Now the arm BD is having 5 ohm resistance and the rest of the resistors is rearranged like that. Now here we need to find what calculate the current drawn from the battery by the network of resistors. Now let us find first whether this bridge is balanced or not. If you take that condition, if bridge is balanced, the current through the arm BD or current through across 5 ohm resistance, so this current value goes to 0. So how we do know that? So for that we need to calculate the ratios of resistance. Now if I calculate the ratios of resistance, that equal to 1 by 2 equal to 2 by 4. Yeah, here the ratios of resistances are equal. So I apply the same formula, P by Q equal to R upon S. If you take this as P and Q and this is R and S. So here the ratios of resistances are equal. Now we can conclude that the bridge is balanced. So when the bridge is balanced, the current through BD arm. So the current through BD arm equal to 0. There is no current which is flowing through BD arm. Now in that case, so this circuit will be changes as, now this circuit I will remove. In the circuit the arm BD, so if we can remove this one, since the bridge is balanced, so this circuit will become same. So the current through the arm BD equal to 0, so that current, the arm will becomes ineffective. Now this circuit will be turned as the above two resistance are in series and below these two resistance are in the series. So we can write that as, again this is 1 ohm resistance in series with the 2 ohm resistance, and along in the down it is 2 ohm resistance along with the 4 ohm resistance. So these things is connected to 4 volt supply. So this is 1 ohm, so this is 2 ohm, and this is 2 ohm, and this is 4 ohm, and A and C. Now the above two are in series and below two are in parallel. The total resistance, again this turns as, so the total resistance it is 3 ohms and at the down it is 6 ohm, and this is connected to a cell of 4 volt. So here I combined these two resistance, 1 plus 2 that gave to me 3 ohm resistance, and the down 2 plus 4 that gives to 6 ohm resistance. So now 3 and 6 are in parallel. Now find the resultant resistance. Resultant resistance R equal to, so that is 1 upon R equal to 1 upon R1 plus 1 upon R2, or you can write that R equal to R1 R2 upon R1 plus R2. So by using this formula, so it is equal to 3 times 6 upon 3 plus 6, which equal to 18 upon 9, which gives to me 2 ohms. So finally this entire circuit is changed into a simple circuit of 2 ohm resistors along with 4 volt supply. Now we need to find the current. So apply the V equal to IR and R equal to V upon I. Sorry, here we need to find I. Therefore I equal to V by R. So what the value I get? I equal to 4 upon 2. So I equal to 2 ohm. Two amperes. So the current which is flowing through the network, is only 2 amperes. See how the network is transformed. So this is the given circuit. So this is the given circuit is equivalent to Wheatstone's bit circuit, and this Wheatstone's bit circuit we understood that. So when circuit is balanced, how did we come to know the circuit is balanced? We check whether the ratios of resistances in this case is equal or not. So we check that. So the ratios of resistance became equal. When ratios of resistance become equal, so we know that the current through the arm, so through this arm, the current through the arm goes to 0. The current through this arm goes to 0. So this arm will becomes inactive. So we remove that, and our circuit now again turn to a series parallel combination of the circuit. So finally we got a simple circuit of voltage and a resistance of 2 ohms. So that leads to calculate the current in the given network. So this is how we need to simplify the circuit. So let's see one more model. So the equivalent circuit combinations we were discussing. Yeah. So this is also one another type model for the Wheatstone's bit equivalent circuit. So in this case, if you draw the network, suppose this circuit is also equivalent to, so the Wheatstone's bit circuit what we draw at here. So this is another model for the Wheatstone's bit equivalent circuit. Suppose if I clear these things, so here the problem is easy because all are given that only resistances. Now this circuit will be turned as, so this circuit is turned to our known Wheatstone's bit circuit. So here we need to find the resistance between A and C. It means we need to find the equivalent resistance. First we need to check whether the bridge is balanced or not. Yeah, since it's having equal resistance, so if you can divide R upon R, which is equal to R upon R, by using the formula P by Q equal to R upon S. So here you take this as P and this Q and this R and this is S itself. Yeah, its ratio equal to 1. So the bridge is balanced. The ratios of resistance are equal. So bridge is balanced. If the bridge is balanced, the current through the arm BD, so through this the current value goes to equal to 0. The current through at here equal to 0. Now the circuit will be turned to a simple circuit. If I draw the simple circuit at here, it only contains top 2 resistance, upper 2 resistors and bottom 2 resistances. And this is connected to a potential difference of 4 volt, and all are same resistance R and R. So this is converted as like this after balancing. Now on the numerator we can get the 2R is resistance, on the downside also we can get 2R is resistance. Again these two are again in parallel, so I can get the equivalent resistance as 2R times 2R upon 2R plus 2R, which is equal to R itself. So the equivalent resistance of the given circuit here itself is R. So this is the one more model for the equivalent circuit of the Wheatstone bridge. So when you see the given network is like this model, so you must think about that. So this is the one kind of the equivalent circuit of Wheatstone bridge. Not only that, so in the previous two models, suppose if you see, so this is the kind of the network which is given. So this is also leads to us Wheatstone bridge network. And apart of that, so the first problem what we discussed at here, so this is also gives to the equivalent circuit to the Wheatstone bridge principle.